Good morning, Verónica.
Hola, Luca. Morning.
¿Todo bien?
Sí, sí. ¿Y tú?
Bien, bien, todo bien.
Menuda madrugada te tienes que pegar cada día.
Y esto para un mes.
Sí, oh, sí, es verdad. Bueno.
Está bien, está bien. Voy aprendiendo yo también muchas cosas.
A ver. And then there is the workshop, right? At the end of May or something like this?
Let me see exactly the days. But yes, it's 1 week. Let me see. 31st of May until the 4th of June. So between May and June, yes.
This is going to be online as well, of course.
Definitely, yes, virtual.
Stop share. Parece que sí funciona. A ver si me he peinado.
Estás guapa como siempre.
Okay. But these meetings by Zoom, you know, they make you more aware that I don't ever brush my hair. They're quite tiring, don't you think?
Definitely. I hope that the vaccination will be very soon for the majority of the population, so we can go back to offices, because I'm still working by home. So.
Yeah, same here. Some people go to the office every day, especially the younger people. They even have lunch together and so on, but it feels like an unnecessary risk, let's say.
Indeed.
Yeah.
I mean, I've been yesterday to the office just to print a few things, but it is just 1 hour every 2 or 3 weeks just to print stuff. Okay, so whenever you want, we can start.
Yeah, we can start. Sounds good. Let me share my screen. Sorry.
Sure. So welcome everybody to these lectures of the Invisible School. Today we have the third lectures on Standard Model in X. Still Veronica Sanz giving these lectures. So let's continue. I think that today you're going to speak about forces. Is this right?
About horses?
Forces.
Yes, that's true. Sorry, my daughter is obsessed with horses. It's like, wow, look at you. Yes, I'm going to talk about horses today, finally. Good. So we are midway in this course. Yesterday, we talked about the space-time symmetries. They are very important. Any theory we have of particles and the forces they experience, it has to incorporate the space-time symmetries. And what we saw is that fermions that you've been taught about and introduced these ideas about the spinorial behavior and the internal symmetries are actually non-trivial when it comes to their properties under the Lorentz group, right? So things that maybe you were told, okay, so you have this gamma mu, d mu, and it looks like you are just contracting these Lorentz indices, so the rest should be fine. In fact, that's not true, because these fermions do also transform under SU2, under the Lorentz group. I wanted to make a clarification from yesterday. I was abusing notation a bit, and I think one of the students kind of pointed at it, but didn't, actually call me off. So I was telling you how the Lorentz group, somebody also said, that is the double covering of SU2 cross SU2. And this way of writing things is very convenient, because we know the the theory of spin that represents the spin of particles is actually the group SU2. So if we take into account representations of SU2, we will be able to write something that is consistent with the Lorentz symmetry because they are contained one on each other. And I was telling you how scalars are 0, 0 within this representation. 1/2 0 representation is a left-handed field. 0, 1/2 is a right-handed field. And I say that 1/2 was a Dirac fermion, but that's not true. Actually, I was abusing notation. What is a right-handed field? Sorry, a Dirac field is taking together a left-handed and a right-handed together. And one nice way of representing it is to precisely put them in a vector, right? But this is just notation. So in fact, the way you should discuss a Dirac fermion under these representations is that it's actually the sum of a right-handed and left-handed field, okay? Not this. This is in fact the type of properties that you will expect from a vector and how they will transform under SO3, 1 or under the covering of SU2 cross SU2. So this is just a clarification because I wrote this and this is not correct. I was abusing notation. So now let's move on into the next stage. We talked about fermions. Fermions are non-trivial, but they are just one part of the standard model, leptons and quarks. And now we also want to describe the other parts of the standard model, which are the force mediators, and those are vector bosons. So what we are going to do today is first talk about, so we went from space-time symmetries. We discovered that those are the Poincaré symmetries, which are Lorentz plus translations. We discussed the algebra of the Poincaré Lie group. And we discovered also that translations were an abelian group, and Lorentz and translations talk to each other. And what we are going to do is move from space-time symmetries or external symmetries that had to do with transformations, let's say, that you can see if you want. A rotation, something you can think about, or as time evolves, how the system is changing. Those are things that you have a human intuition about. But as you know from quantum mechanics, there's a lot more in nature that can be seen by eye. And there are also these internal properties of your fields or your quantum fields. And the one that you have been taught about a lot, I'm sure, is precisely spin, because it determines the properties, the thermodynamic properties of these fields. So what we are going to start with is talking about global symmetries. The meaning of global symmetries are transformations on the fields. So let me call this field psi. It can be anything. It can have any kind of spin. I'm not determining anything. This psi might depend on space and time. But what I'm going to do is to explore how the properties of these fields change when I simply make a transformation on this field. And where this transformation does not depend on space and time. So the meaning of global is a space-time meaning, is that it's symmetry transformation that does not depend on the coordinates. Okay, so spin is a particular case of that. Okay, so in order to think about these global internal symmetries and to get a better intuition, we had to remind ourselves something that you've probably seen in mechanics or later on. And if not, please do go and check it out, which is Noether's, and anybody that is German is probably like putting their hands like this, Noether or whatever the way you say theorem. So Emmy Noether, mathematician, who stated that if you have a system and this system has a symmetry, there will be consequences. And the consequences will be many. In particular, there will be conserved quantities. So Nutter wrote down the way to understand how the presence of invariants, of symmetries, leads to something physical that we can observe, which are conserved quantities. Okay? So the idea is that if you take, in our case, in particle physics, we think on actions or Lagrangians, which is the integral of over space-time. And Lagrangians depends on fields. So when I do transformation on these fields, for example, like these ones, what I'm going to do is to change the Lagrangian, right? The Lagrangian is going to go to the one we had before, plus some variation, right? So my new Lagrangian, once I've done some transformations on my fields or my space-time or whatever I've done, is going to lead to a new Lagrangian that will be the one we had before plus some modification. So we separate the previous one and the modification. Okay, so if this Lagrangian, so if this theory preserves the asymmetry, so what it means then is that under those transformations, the Lagrangian should be the same. So delta of the Lagrangian under this transformation should be 0. This is, again, let's go back a second. The action, the Lagrangian, does determine the behavior of our fields. Minimizing this action or analyzing the Euler-Lagrangian equations for this object leads to the behavior of our fields, to the laws of physics. So if I start modifying my fields under some transformation and I see that my laws of physics stay the same, or what I'm saying is that the nature, these laws of physics preserve asymmetry, respect asymmetry. That means then that under these transformations, the Lagrangian stays the same, the laws of physics stay the same. It's all equivalent, okay? Very good. So, but we know what this variation of my Lagrangian is going to be. If this is equal to 0, using the Euler-Lagrangian equations, I know that I can write this. So let's say that I'm doing some kind of transformation X, whatever. Is this U, is a phase, is whatever kind of transformations. I know that I can write this as derivative mu of the variation of my Lagrangian respect to the derivatives of my fields, whatever the fields are, psi, phi, whatever name you want to give, and multiply by how the fields themselves change under this transformation. Okay, so that's Nutter's theorem. This is just saying that the invariance of the theory under a transformation X can be rewritten, that condition can be rewritten as this, which is the dependence on the Lagrangian on the fields themselves and how the fields do change. Now, this is something, that part here depends on a Lorentz element over here, or a Lorentz index, mu. So we can actually write this as derivative mu of J mu equals 0, where J mu is precisely this thing over here. So the invariance of a theory under a symmetry transformation is equivalent to the conservation of a current J mu. It's a four vector. And the fact that this guy does not change with mu. This has lots of consequences. For example, we can think on particularizing for mu equals 0, right? And then this equation here leads to the conservation of a charge Q, a generic charge, it's not the electric charge, it's a charge Q, which is defined as the integral over, let's say, 3 dimensions of this current 0. And that the property of that charge, this equation of conservation of this current means that that charge does not vary with time. So what it means is that if there is a symmetry, if we identify a symmetry, a transformation of our fields that leaves the equations of motion invariant, we, of course, realize that there is something deep and interesting of our system, but in practice, what it means is that there will be a set of conserved currents, those ones, and in particular, there will be quantities, charges, or generalized charges, which do not vary with time. So invariance under space-time symmetries lead to the conservation of momentum and energy, which we know in mechanics in closed systems, that's what we get. Conservation of a current of in electromagnetism leads to the conservation of what we call the charge, the electromagnetic charge. For example, we cannot have a process where we go from an electron to, I don't know, a neutrino and let's say whatever, a W plus or something like this, obviously, no? You are used to think that in any process, in any interaction, there should be a conservation of electromagnetic charge. So as time evolves, as this transforms into this, the overall electric charge should stay the same. And this, of course, violates this. So this concept of conservation of electric charge is something that you need to now think in a more generic terms. The presence of asymmetry will lead to the conservation of a set of charges. And one of the consequences is that as time evolves, there will be then any process that you can think of has to preserve those quantum numbers. Okay? So Nether's theorem, very important to actually understand what are the deeper consequences of symmetry. Okay, so let's start with global symmetries. And to think about global symmetries, we are going to do a particular example. So we are going to use a scenario, which is nuclear physics, to illustrate the use of global symmetries and how much power do they have. Okay, so nuclear physics, remember, you probably know about quantum chromodynamics. Since you are here in this course, you know about mostly high energy things. And you might not know so much or study too much nuclear physics because this is kind of like low energy and dirty and so on. But the truth is that QCD, quantum chromodynamics, it has a very different behavior at high energies and at low energies. And high energies, the important degrees of freedom are going to be quarks and gluons. And their color properties are going to be apparent. So when we think, for example, on the Large Hadron Collider, or we think on early universe, we can think on scattering of quarks and gluons. But at low energies, the behavior QCD is very different. The correct degrees of freedom to describe the theory are actually baryons and mesons. Baryons are particles that are fermionic or that have a spin half integer. And there are many, many mesons as well in the low energy spectrum of QCD. For example, pions, kaons, and so on. The rho meson, the A1 meson, the F2 meson, things like this. The most important baryons, of course, in the low energy QCD are actually the baryons we see in the nucleus. So protons and neutrons. So understanding the properties of QCD at low energies, understanding the properties of protons and neutrons and why they form nucleus, right? So it's made of protons, neutrons, and little balls or whatever. This is the way our atom actually is made of. And we know that what holds together the protons and neutrons inside the nucleus is precisely the nuclear interaction. The nuclear interaction is a low energy expression of QCD. So the tools you will need to understand nuclear physics are different than the tools you will need to understand QCD at high energies and scattering of gluons and protons, gluons and quarks. What we would like to do is to write down a Lagrangian that tells us how protons and neutrons interact with each other, how do they form nucleus and how they stay together, and so on. So we would like to have a Lagrangian that contains protons and neutrons as their fundamental degrees of freedom, as the important degrees of freedom. The same way that we think on QCD interactions as being some kind of ion exchanges, let me use the same, of gluons between quarks. So this is a gluon, right? At low energies, we will like to think about nuclear interactions as being exchanges between protons and neutrons, and the main particle exchange over there is precisely pions. Okay? So we would like to describe the nuclear interactions as a theory that contains protons and neutrons, but also pions as their force mediators. Okay, so let's start. From the point of view of the nuclear interactions, the proton and the neutron are the same. To the nuclear interactions, what they care about is the baryon number that they carry, and protons and neutrons are from that point of view, from the point of view of those interactions, they are the same. They are not exactly the same. We know that because the proton has electromagnetic charge and the neutron is neutral, no? So we know that from the electromagnetic interactions are going to change this duality between protons and neutrons. We also know that the mass of the proton and the mass of the neutron are not exactly the same. The proton is slightly lighter, as we were discussing yesterday, right? And that's what makes the proton to be the stable particle and not the neutron. The proton being the lightest with baryon number stays stable. And but this mass difference, this delta M proton neutron, is quite small. So we would like to write down a theory that accounts for this invariance, if you want, between being a proton or a neutron. Okay, so we start with a Lagrangian that contains a proton and a neutron. Those are baryons, they are fermions. So you will have a Lagrangian that is actually something that contains the field proton derivative mu of the proton minus some mass for the proton, like this, right? And you will have exactly the same from the neutron. Now, since these two masses are so close to each other, let's say that they are the same. Let's put them to say that they are exactly the same. If they are the same, then we have a kinetic term for the proton, one for the neutron, and the same mass term touching the proton and the neutron. Is there a way in which we can write this Lagrangian in a more compact way? So let's try to do that. For example, let's do the following. Let's take a new field and write it as a vector that contains the proton and the neutron. So a field that contains two components, that says 1 and 2, where the first one is, for example, the proton, and 2 is the neutron. Okay, so think that now it's me who has decided to write down this field as pairing up or clamping together the proton and the neutron. These guys are by themselves fields with all their degrees of freedom and their Lorentz properties. Okay, so it's me who is decided to write it this way in a more compact fashion. So then this Lagrangian of protons and neutrons can be written in a more compact way. I have an I here as I times psi bar derivative psi minus this common mass psi bar psi. Okay, so we're now the psi bar here represents the proton plus and the neutron plus. Okay, it's just the transpose of these bar fields. So for the moment, it looks like I've done nothing. I've just taken a Lagrangian that contains two types of particles. I know that these particles are related in some way because they actually suffer the same interactions, and under those interactions, they are felt as the same object. So I've formalized this similarity by clamping them together in one single field. And by doing that, I get this Lagrangian. You see, I'm just massaging things for the moment. But in physics, that's what we do a lot of the times. We try to look at the same thing from different perspectives in case this new perspective gives us some insight that we couldn't see before. And this insight was hidden by, complications on the way we were representing things. So changing representation of things is important. Okay, so let's do that. We do that, and then we realize that actually, if I say, for my new field, psi, if I now transform it by some unitary transformation, unitary because protons and neutrons are quantum fields, their probability, their norm has to be preserved and so on. So you need to do a unitary transformation. So I do that. Then I realize that this is a two-dimensional object, right? So this unitary transformation will be 2 by 2 matrices with a set of properties. And these unitary matrices then belong to a group that is unitary rotations in 2 dimensions. Okay. So what is the procedure? You just state this. You say, let me transform the fields. Then I write a new Lagrangian, L prime, where I see psi, I write a new psi prime with this U. And then I get stuff like I get I times psi prime, then U dagger, derivative, U psi prime, sorry, without the primes, minus n times U dagger U psi. Okay, so when I change from the original fields to the transform fields, what I get is a set of U's inside. Since these are, yeah.
But are you taking M as equal for the proton and neutron in this case?
This psi guy?
No, the M.
Yes, exactly. Yeah.
Okay, so you're in the limit in which MP is equal to Mn.
Exactly.
Okay, thank you.
Yeah, so these two are the same. Perfect. So for the moment, I'm taking, what I'm doing is taking this Lagrangian and examining what kind of transformations will lead the Lagrangian the same. What are the symmetries of my Lagrangian? And for that, I'm probing these kind of transformations or unitary matrices. So indeed, this Lagrangian will be the same as the original Lagrangian, if this is equals 1, so the unity in 2 by 2, right? Then this will essentially go to 1. Since there is a derivative here, right, that's something that depends on space-time, I'm going to then assume that U does not depend on space-time. It's a global modification. And if I do that, then this U can go and stay here. And we get U dagger U equals 1. That condition leads precisely to this disappears and this disappears. So under rotation U of my fields, my Lagrangian stays the same. So this is preserved as long as the U's, these transformations satisfy this property. Those 2 by 2 matrices whose U dagger U is equals 1 is precisely the group called U2, unitary transformations in 2 dimensions. Okay, so by simply rewriting our Lagrangian in a new way, where the proton and neutron are lumped together, and where the masses then are put as the same, we realize that there is a symmetry of this new field. There is an invariance, which is any kind of transformation that rotates my field, my nucleon. So these are protons and neutrons are nucleons. They are called nucleons, both of them. So where my nucleon field is actually rotated by a U2. Okay, so that's an invariance. And since there is an invariance, there is a symmetry of my system, there must be consequences. So let's examine these consequences. So first, we think on this U. Now we realize that that kind of symmetry transformation has to be belonging to a group called U2, unitary transformations, that precisely gives this condition. That ensures that my Lagrangian stays the same, that delta Lagrangian is equal to 0. Okay. But this is not the best description because this unitary transformation, U dagger U equals 1 is nice, but it is more, let's say, it's more interesting if what we do is the following, is we take U, these possible transformations, and write them as unitary transformations with determinant 1 and the possible phase of my unitary transformation like this one. Okay, so what I've done here is the following. I'll say that this U2 matrix can be decomposed as a SU2 matrix, meaning a special unitary, so with determinant equals 1, times a phase. And this phase is precisely what in group theory is called a U1. Unitary transformations of one dimension, simply a phase, a complex phase. What I've done here is to say that the U2 symmetry transformation I want to understand for protons and neutrons from nucleons is actually isomorphic to 2 transformations, a U1 times an SU2. So I'm back to something we discussed yesterday. We have SU2, famous SU2, all the time SU2, theory of spin, theory of rotation, theory of many things that, that relate to each other, and we have a trivial phase, a U1. So now I know that there are 2 types of symmetries that affect that are present in the nuclear interactions, a U1 and a U2. So we have 2 types of symmetries. We are going to have 2 types of consequences. And this is indeed what happens. If we think about the nucleons, the nuclear interactions, now we know that there is a theory, those are theories that have an SU2 cross U1 kind of symmetry. And then each of these symmetries will have a neutral current associated with them. For when it comes to SU2, the current, now we have an index for each of the generators. Sorry, let me put the mu. And just following neutral, we say, well, this current is built by taking the Lagrangian, see how this Lagrangian depends on the derivative of my nucleon field, and then looking at how my field, my nucleon, changes with SU2. Okay? And what my field is going to do with SU2 is simply change by the SU2 transformation, sigma I over 2. This is just the I and the 2 are simply, you know, for how to say, notation. It's not super important. Field. So to know how this field changes under SU2, the only thing I need to do is to expand this at low order, at the first order. So what this is going to lead to, so I put a parameter alpha, possible parameter over here, is the same derivative of the Lagrangian respect to psi. This is something we can compute. We have computed many times in field theory and so on. And then this first order is going to be precisely I sigma I over 2, the Pauli matrices times I. I don't know if you have any questions so far.
No, there are no questions yet.
Perfect. Okay. So it's this. If I expand, psi prime is now exponential of I alpha sigma A over 2 psi. And the only thing I do is to expand at first order to obtain this variation. Very good. This is something you can compute easily because you know your Lagrangian, and this leads to this particular structure. So it gives to psi bar, gamma mu, sigma I over 2 psi. So this is the current that is conserved due to the SU2 invariance of the nuclear interactions. And you see it's a current that has three components, the three sigmas. For each sigma of Pauli, sigma 1, sigma 2, sigma 3, we get a particular component of that current. And what we know is that d mu JA is going to be conserved. Very good. And for the U1, it's even easier, right? This guy doesn't even have an index A. It's simply the modification that comes from an alpha, or just from a phase, sorry. And this J mu, same story, is derivative respect to d mu psi. This is going to stay exactly the same. And now the variation is simply I psi. So in total, we are going to get minus psi bar gamma mu psi. All right, so we find two particular combinations of our nucleon fields that are going to represent conserved currents. This SU2, that particular SU2 that is preserved by the nucleons is called isospin. When people discover these properties when studying nuclear interactions, because it's represented by sigma A, by the Pauli matrices, it does behave exactly as a spin. So they wanted to call it whatever spin, and they call it isospin, where iso, I guess it means duality between proton and neutron. The U1, which is simply a phase, is very important. It's actually called the baryonic current. So when I've been talking about how protons and neutrons carry baryon number, and how this baryon number is important, well, it's crucial to understand the stability of the proton, is precisely related to this, or due to this baryon current. So the conservation of this baryon current and look at this baryon current is a four-dimensional quantity, a 4D vector, is going to lead to the conservation of a charge, and that charge is going to be precisely the baryon charge. This is precisely the typical intuition that you do have about quantum numbers under conservation. The quantum numbers are simply assignments that you do to fields to represent the conservation of currents like these ones with time. So when, for example, the proton wants to decay, it has to decay to another object, since it has baryon number equals 1, has to decay to another object that has baryon number equals 1. Otherwise, it can't, because baryon number is conserved through time, and that also means that it's conserved in any kind of decay or process you're thinking of. And since the only other guy available is the neutron, and the neutron is heavier than the proton, kinematically this is not allowed. So energy momentum conservation, another symmetry, another consequence of Lorentz invariance, does not allow this decay, and then it's not possible. The proton remains stable as a particle as far as we know. Okay, cool. So this is something that allows us to understand the properties of these nucleons, how they are going to decay or not, how they can interact or not with each other. And the conservation of these currents leads to that in processes involving nucleons, there will be some selection rules on how this is possible. In particular, for example, once you start thinking, let me go to a new page, thinking, yeah?
Veronica, maybe before you go to the new page, no worry. There is a question. Do we always look for further decomposition of the groups?
In general, yes, you want to go into an irreducible decomposition of your group. So U2, the original one, was not irreducible. You could reduce it to smaller groups. And you do that in order to clarify, to make it more clear what kind of fundamental symmetries you are dealing with. So the answer is yes, you always do that.
Okay, thank you.
So once you have identified the presence of this isospin symmetry or isospin current that is conserved, or the baryon number current that is conserved, you start thinking about conserved currents. So for example, when you think about nucleons, you have to think of whether they have a positive or negative baryon number, what kind of processes are allowed, and so on. But also, you start thinking about the isospin the same way that in quantum mechanics you thought about spin of a particle, of a fermion, and represented it as something that had to do with these Pauli matrices. Isospin will be another property of these nucleons, a property that has nothing to do with the spin of the particles, it's just a new one, and which is also represented by Pauli matrices. So anything you've done before in quantum mechanics, for example, you remember how the spin and the orbit of a particle were related to each other, on how spin and the possible external magnetic fields will interact with each other. All this stuff that you learned in quantum mechanics, like the Zeeman effect, which you felt, for example, looking at the spectrum of these baryonic excited states and so on, or the excited states of an atom. Now you can look at the nuclear spectroscopy and search for these particular processes as well. Okay, so the same story that you did in atomic physics, knowing that the particles there have a spin, now you can do in nuclear physics, now knowing that there is an additional symmetry, an additional property, which is this isospin, that will lead to similar effects that then you can explore at that level and exploit and so on. Imagine all the applications that this nuclear Zeeman effect has been led has led to. Okay? So this understanding that in the nucleus we have protons and neutrons, and although they look different, the neutron decays, the proton doesn't, one has the electric charge, the other not, the mass is different. But once you go a bit above and say, okay, the mass is different, but not that different. So at first order, let me assume that the mass is equal. Then I start seeing dualities and interesting things that relate to each other. So in particular, once you've done this assumption that delta, the mass difference between these two is 0, so the mass of the proton is equal to the mass of the neutron, then we see that there is an SU2 cross U1 symmetry. And we can start extracting all kinds of consequences of this symmetry. But once you've done that, which is the first step, you can actually go back and say, okay, but what if now I don't want to do this? I say that this is not 0. It's small, but it's not 0. This is 2, it's much less than the mass of the proton or the neutron, but it's non-zero. So the way to incorporate these realistic effects that had to do with the fact that this symmetry is an approximate symmetry. It's not not an exact symmetry. It's okay because I know that if my symmetry was exact, I know that this current will be conserved and then I will get all these important consequences. But what if my symmetry is not exact? Well, what I would expect then is to say that this is, okay, it's not equal 0. When it's approximate, this current will not be exactly conserved, but this non-conservation has to be a function of the mass difference between these two things. Because I know that as delta M goes to 0, the current should be conserved. Okay, in nature it's non-zero, fine, but it's small. So this allows me to parameterize the breaking of this symmetry, this isospin and baryon symmetry in a consistent way. I know that whatever it is proportional to delta M to some power. And since the mass has dimensions, this dimensional analysis will give you a lot of intuition of how to incorporate the breaking of that symmetry in a consistent way. Okay, so this is led to a very successful low energy description of the properties of nucleons. But we are going to go one step further. We are going to say, fine, but you told me that nucleons also, the way they do actually interact with each other is through the exchange of these pions, no? That's what you thought, that the length of the nuclear interaction is actually related to these pions and their mass and so on. So how do you incorporate these effects? How do you actually write down an interaction between a pion and a nucleon when I know that the Lagrangian of the nucleons is well described by this symmetry property? Whatever I write down, which is an interaction pion nucleon, has to also preserve these symmetry properties. Okay, so in that context, the pions come in and we need to make it fit with our description, can we? So what we are going to see is that symmetries, again, tell us exactly the way this has to be done, and there is no other way. So it determines completely how we need to write down these interactions. Okay. So let's do that. Let's go then to another sector. We talked about nucleons. Let's talk about pions. Pions is another element of low energy nuclear physics. No, there are these particles. The mass of the pions is very, very small. In fact, there are 3 of them. We have pi 0, pi plus, and pi minus, 3 pions. Neutral, positive and negatively charged. Electromagnetic interactions. And indeed, the mass of the neutral pion and the mass of the charged pions is very similar. It's not exactly the same. One is 135 MeVs, more or less, and the other is 139.6 MEVs. From the point of view of the nucleons, remember they are much heavier. These masses are not that important, and their mass difference is even less important. So again, we are in a situation where the mass difference between the neutron and the charge is much less than the mass of each of these pions. So we are going to again use this semi-degeneracy in these states to try to extract the presence of new symmetries. So let's do that. Okay, pion is a spin zero particle, is a scalar state. And the Lagrangian, we know how it's going to be written, will be 1/2 d mu pion 0 d mu pion 0. This is again the only possibility we can write down consistent with the symmetries of space-time. And we can write the same for the positive and negative pions. That's the kinetic term. And then the mass term, it will be like this, pi 0 squared. And the same for the positive and negative. So what we got here is a Lagrangian that contains pi naught, a Lagrangian that explains how pi plus and pi minus interact. And we are just summing this over. Same as in the case of the nucleon is, if we now assume the masses are the same, which they are a first order, do we see a symmetry structure coming in? So same as before, what we are going to do first is to define an object, some object that puts together the three pions, pi naught, pi plus, and pi minus. The problem is that if we just try to do this, write an object, a field that is just these three guys, the interactions are not that nice. Remember that anything like the mass term for the pion, plus minus, is precisely a pi plus, pi minus, and so on. So the first thing we need to do is to redefine the fields. So we define the pi plus as 1 over square root of 2 psi 1, a new field, psi 2. And then the pi minus, which is the complex conjugate, will be 1 over square root of 2 psi 1 minus psi 2.
Veronica, sorry, yeah. Just because it is related. How do you know that the pion have power 1 in the Lagrangian, like a scalar field?
The pion is a scalar state.
Fine.
No, sorry, when the pion is discovered, so as a state, what you see of the pion is how it decays and how it behaves, and their properties are consistent with a scalar state. So that at the beginning, you just see a state, and then you start examining their behavior and see that it's only consistent with a scalar state. If this student's question or something is, if you go and look at the PDG, the particle data group, they always have summaries of each of these particles, the best we know of these particles, and you can look for the pions, see what are the typical decays. So how they were discovered is how they decay and so on. And you see that it's only consistent with this spin zero hypothesis. So here,
maybe a related question that can help understanding: are all the mesons that one can construct always scalars?
Meson, the name means scalar in that case. So what we know of, or what we assume, is that the pions are bound states of quark anti-quark. They are bound states that do not, let's say, of QQ bar. This is a scalar spin zero state. Remember that, for example, the mass of the fermion, or anything that appears in the Lagrangian, any object that appears in the Lagrangian, has to be a singlet of everything, So the mass term is a psi bar psi is a spin zero state. So pions are bound states of QQ bar. And for example, you could also have a row meson, which will be actually a vector field, which are bound states of this type, which under the Lorentz symmetry, they do behave as a vector.
Very good. And a related question to what you were writing right now, if you can repeat why there are no pure mass square terms for the mesons, but there is a mixing.
So the mass of the pion 0 goes like this, as you would expect, pion 0 square, and this is my mass, sorry. But if I try to write mass of, I don't know, pion plus as pion plus square, that mass term has charge 2. So violates electromagnetism. I always had to write things that are, again, a mass term is a term in the Lagrangian, and the terms in Lagrangians have to preserve everything we know is conserved, every symmetry, including electromagnetic charge. So it has to go as pi plus, pi minus to make sure this term doesn't violate electromagnetism. It has 0 charge.
Okay, very good. There are no other questions. Thank you.
Thank you. Cool. Okay, so we are now trying to clump together in a consistent way all these 3 pions. But what we see is that this description in terms of pi plus and pi minus is not that great. Each of them, actually pi plus and pi minus, we know are related to each other. One is the, let's say, field anti-field, right? So can we make this more apparent? It kind of disentangle this pi plus, pi minus component. The trick will always be the same, like anything that is charged and you want to make it in a simpler way, it will always be like this. So this charge thing will be a complex parameter or a complex function, and you can rewrite it as a real part and an imaginary part. So when you have a complex scalar field, you can always do that, where psi1 and psi2 are assumed to be real functions. And then the pi minus, then the complex conjugate is going to be this times this. Okay? And then the pi naught, this third state, I can just call it psi3, just to use the same notation. So now, instead of talking about pi naught, pi plus, and pi minus, where I know these 2 are related, because this is a complex function, but they are related, I use a more convenient notation, a reparametrization of my fields between psi1, psi2, psi3. Okay. So let's see how, written in terms of this new parametrization, how things look. All right, so in terms of this new parametrization, and again, assuming the masses of all pions are the same, I get a new Lagrangian. That is the one I had before. But now I can write it in a more complex, in a more compact way. Right? Where I is simply 1, 2, and 3. Okay, this looks nice. It's more compact. In one line, I've written the whole Lagrangian. But this is, again, beyond aesthetics, is now you start writing things in another way. You start seeing behavior that it wasn't apparent before. In particular, why don't I do something? I write a vector made of psi1, psi2, psi3. I take this vector, right? And I rewrite my Lagrangian in this form. I say that this is equals to 1/2 d mu psi transpose d mu psi phi, sorry, I have problems with very good, phi transpose mass square phi. So you see, I've written exactly the same thing I had before, but in a more compact way, where I define this vector of 3 components. So this now contains 3 real functions, psi1, psi2, psi3, and those are reparametrizations of my initial pions. This form of the Lagrangian Now it has like a structure because we are talking about a vector. So we can start thinking of what kind of transformations we can do on this three-dimensional vector that will keep the Lagrangian the same. In particular, let's say that I do my field goes to some transformation. So that's my new field. And I introduce this in my Lagrangian. Okay? So in this part, we are going to get, if O is again a global transformation, so it does not depend on space-time, these derivatives will not do anything on those. This first term will then have O transpose O times the original Lagrangian, 1/2 d mu psi transpose d mu psi transpose. Psi. And this second part, the same, will have exactly the same. So if I impose or I search for transformations such that this is equals unity, now in 3 dimensions, then those transformations, those O's, are precisely symmetries of my Lagrangian, symmetries of the pion properties. So the kind of three-dimensional matrices with real parameters that satisfy this are precisely a group that is called orthogonal transformations in 3 dimensions, which is simply our usual rotations in 3D. The intuition that you had about taking a point in a space-time and rotating it, now you can think and apply it to this internal space of your pions. In this particular representation, you can rotate these fields with orthogonal transformations, and you will get exactly the same physics. So this invariance, this symmetry, must lead to consequences. So let's try to see that. What consequences are those? Now, in terms of the properties of the pions, again, having a current, a symmetry of 3 will lead to a current. This current will be conserved by the pions, and then it will lead to selection rules and so on, just related to the pion dynamics. But the thing we would like to understand is how we understand now the Lagrangian of pions. We understand now the Lagrangian that corresponds to the nucleons. But what about anything that has to do with interactions between nucleons and pions? So we know that the Lagrangian of nucleons have a symmetry U1 crosses U2. So anything we write about nucleons have to preserve that symmetry. We know that the Lagrangian, the theory of pions, have a symmetry of 3. So we know that anything we write about pions, including any possible interactions, have to preserve that symmetry. So we need to find a way of writing a Lagrangian that involves pions and nucleons that preserves the U1, the SU2, and the O3. Can we do that? So we are fine. Yes, we can, of course. Otherwise, I wouldn't be telling you about this story. And we can because of this property of isomorphisms. O3, these orthogonal transformations in 3 dimensions, and SU2, this theory of spin and so on, they are different things. They apply on different objects. For example, these guys, the generators in Jungian, are the polymatrices, complex. They act on complex functions. In our case, it would be in 2 dimensions. These O3, also they are acting on this nucleon. These O3 are actually related to the generators, right, of rotations in 3 dimensions. There are 3 by 3 matrices acting on this pion field. They are different groups, but at the same time, we do know that although the Lie group is different, for both these groups, the Lie algebra is the same. This is what we were discussing yesterday. You remember the Lie algebra of rotations in 3 dimensions had this infinitesimal structure. Remember, it had the local level at infinitesimal structure that is JC. And I had this Levi-Civita over here. But this is exactly the same that the SU2 does. It has the same Lie algebra. The objects that corresponds to O3 and SU2 are different. Here we're talking about 2x2 or 3x3 matrices, but at the level of how these guys commute of their algebra, the structure constants of both groups are the Levi-Civita. So this is going to be our key to understand the way we can actually write down consistent interactions between pions and nucleons and that preserve all the symmetries that we are supposed to preserve. So in particular, there are 2 types of terms that we can write that involve nucleons, baryons, they are spin 1/2 particles, so they have, they are spinors. If we want to write something that is consistent under Lorentz invariance, we cannot do whatever. We need to write things like this. For example, when all the spinorial indices are contracted, then a term like this, and then a term like this, where these semi are the polymatrices with A1, 2, 3, and these phi A are the pion fields 1, 2, 3. So this contraction of the SU2 indices will be allowed. This whole term of interaction will be possible and will be invariant under all the symmetries of both pions and nucleons. And we could also have another term. For example, there's only another possibility, which is psi, sigma A over 2, same story. Psi, again, the phi A, so these guys contracted, but you can actually put a gamma 5 over here. So when we think on Lagrangians that we can write down that have fields that are pions and nucleons that are consistent with the Lorentz structure that you expect from that you have on fermions, there are only these 2 possibilities that are also consistent with these global symmetries for pions and nucleons. Now this is it will be a scalar type of interaction, and this will be what is called an axial type of interaction. In principle, from the point of view of the discussion I've done before, these 2 are perfectly valid. But there is another property of the pions that again was discovered through their decays, is that they are CP odd particles. So they are scalars, but with CP odd properties. In this case, they are called pseudo-scalars. And these pseudo-scalars, if you take into account the CP properties of these pions, then this is not a good description of their properties, and this is axial interaction is the only way the pions can talk to the nucleons. So this is precisely the interaction that we were looking for. It will be proportional to some number, Fa, and the structure of this interaction will be this one, and none another, okay? So we can then use this Lagrangian precisely to take into account all kinds of properties for pions and nucleons and describe, at low energies, how these pions and nucleons do interact. So, okay, so I'm going to stop here for global symmetries. All these stories of the pseudoscalars, of course, nuclear interactions may not be your prime interest, but all the tricks are just done. The tricks that people used many, many decades ago to describe consistent nuclear interactions are tricks that we use all the time when we do model building. When you think about, let's say that there is a new particle with those properties, what kind of interactions they could have? This kind of analysis we've done is precisely the analysis you would do as well. All right. And it will determine the allowed interactions and the ones that are not possible. So symmetry is, again, very, very important. So,
yeah. Question. So the scalar term is rejected only because of the experimental results?
The scalar term is rejected because through the experiment, we know that the properties of pions, the GCP properties, are the J, we know is a scalar, so it's 0, and CP is a CPO particle. So by studying the way the pion decays, the angular distributions of this pion, we know that is a scalar, and we know that it's not just any scalar, it's a pseudo-scalar, so it's CP odd. The same way that the Higgs is a CP even particle, the pions are CP odd particles. There's a lot more that I could tell about this that is related to the actual origin of pions as pseudo-Goldstone bosons and so on. But since we are going to go through this Goldstone theorem, I'm not starting with this story yet. But yeah, because of the CP odd properties of the pions, which are determined via decays, then we know that from these two possibilities, these two are consistent with the O3SU2 properties, that one has to be rejected because it's not consistent with a CPO particle. All right? Okay, and this kind of analysis you can do, again, in any model of new physics, or when you, for example, are considering extended Higgs sectors and so on and so forth. The way to write things, to write it in a vector way, so that now you know that the transformations on that vector will be some kind of matrix, allows you to then understand what kind of group properties are behind. So I'm going to move towards these forces. The forces of the standard model are actually a consequence of trying to generalize a global symmetry into a local symmetry. So let me, follow the whole path. Yesterday we were discussing about our fermion fields, right? And we know that thanks to Lorentz invariance, we know that the only terms we can write for a Dirac field is this psi bar, I, gamma times derivative, or d slash, whatever you prefer, and a possible master. So these are this is the Lagrangian we can write them. Where now psi is our usual Dirac field, so you can think on psi as an electron or a muon or whatever Dirac particle you want to consider. Okay, so does this Lagrangian, apart from preserving Lorentz invariance, does this Lagrangian have any other global symmetry or any symmetry, any global symmetry? Well, since this guy has a bar here, and the bar involves some gamma matrices, but also complex conjugate, and here is psi. If, for example, I do the following, I do psi goes to a new psi with just a phase. Let me do with minus phase. Just say that I want to examine whether if I rotate my electron field by a complex phase, what happens to the laws of physics. And since here we will get exponential of I theta, and here we will get exponential of minus I theta, the whole Lagrangian is invariant. This theta, this phase, drops out. What it means is that the Dirac fermion fields, the fermion fields, have a symmetry that is a U1 symmetry, just a complex phase. just a simple rotation of the field. What are the consequences of having this U1 symmetry? They will have an associated conserved current and an associated conserved quantum number. You might have not heard about this before, but it's something that you assume all the time. And this conserved quantum number is called fermion number. What it means is that, for example, when you are thinking on any kind of interaction, you say an electron goes and interacts with a photon, or a quark with a gluon, or stuff like this, or that's whatever, right? Any kind of process. And remember that when you do quantum field theory, I assume most of you have done it, you put this little arrow over here, right? And this arrow, for you, is how sometimes you might think that this arrow corresponds to having the electron moving in that direction. But then when you have to do an electron, you do this. When you have to do a positron, you probably put the arrow in the opposite direction. No, maybe you have this kind of notation. And maybe you have been taught about this from the point of view of this is convenient because you can think on the positron as an electron that is moved backwards. It sounds like a strange thing, but you do it anyway. But in fact, all this is code word for making sure that when you write a Feynman diagram, there is a flow of something called fermion current. And you need to make sure that in any diagram, this fermion current is not disrupted. Why is that? Because precisely any fermion has a conserved quantum number that is, or a conserved current that has to do with this fermion properties. Whereas you don't do this for scalars or vectors, you do that for fermions. You put these little arrows for fermions. And when you, for example, you've been told that for the positron you do the opposite, it's not because the positron is moving backwards, it's actually because the fermion flow is in the opposite direction. It's the antiparticle, okay? So there is this conserved U1 current that has to do with just any kind of Dirac fermion. And the typical current then is, if you do exactly the same analysis with them for the nucleons, you will get indeed that has this form, and the conserved quantity is precisely what you will call charge or electric charge later on. Okay. Now there is even another type of symmetry you could think of. What if I now set mass equals 0? What if in this Dirac Lagrangian I set the mass to 0? Apart from the symmetry I already had, do I have a new symmetry? So let's see. Now we have psi bar, I, gamma, derivative psi. Now the only difference is that I don't have this mass. The structure is a tiny bit more, the structure left is something that involves these gamma matrices. So maybe I can find some new symmetry. So this guy, of course, has this symmetry already. But if we set it to 0, the mass, do we get an additional symmetry? And the answer is yes. Thanks to this gamma over here, we can also say that if I take the field and I rotate it by, now instead of just a simple phase, I put a gamma 5 over here. This is also a symmetry. And this is a symmetry that is only good or is only exact if the mass is equal to 0. So massless fermions do have an additional symmetry, which is the usual, for you, chiral symmetry that you probably heard about and you used when you think about high energy collisions and so on. At high energies, where the energies involved, the momentum involved is large, this mass presence is not that important. And there, an approximate chiral symmetry appears, and that leads to selection rules like chirality. And you probably, if you do Peskin-Schroeder, for example, the quantum field theory course of Peskin and Schroeder, there is a good description of how these massless fields, which are only approximately massless, what kind of new selection rules you will expect. Okay.
Veronica, a couple of questions. What is the difference between the U1 fermion number transformation and the U1 electromagnetic charge transformation?
None. For the electron, this fermion number and the conservation charge are precisely the same as the electromagnetic charge conservation. I think in the discussion of yesterday, we were saying how when you have a charged particle, which is most of the particles in the standard model, you have to consider a Dirac field. Because electromagnetic interactions preserve parity, so you actually need to consider a left and right-handed field, so psi, to describe a charged particle, something that is consistent with electromagnetic interactions. You need something where left fields and right-handed fields are treated at the same level. You need to put them together. And that's what leads to a Dirac field. And that's the Lagrangian of the Dirac field. So that Lagrangian of the Dirac field is a consequence of electromagnetism. So that fermion number, in the case of this, for example, an electron, a proton, the particles of the standard model we know of, that conserved quantity is precisely the electric charge.
So in the case of the baryon or the quarks, just to generalize, the electromagnetism should have different constants with respect to the baryon number. So in this case, we can really say that there are different symmetries.
Exactly. Yeah, exactly.
Another question. In this case of massless fermions, if there are more than one psi, then the most general symmetry of the Lagrangian, what will be?
Very good. So that's what happens actually in QCD, the QCD Lagrangian. When you think on quarks, you can think your QCD Lagrangian as having, let's say, a psi bar up. The same for down, the down, charm, strange, and so on. And then you will also put masses for them, right? Up, down, and so on and so forth. Now imagine that now we neglect all the masses because we think that for the QCD interactions we are dealing with, the masses are not that important. Or we put them all together, 0 or equal or whatever. Then we can play exactly the same games we've done for the nucleon, and we can lump together in a new field, psi, my psi up, my psi down, my psi whatever. You want to keep the charm, the strange, whatever number. And write this Lagrangian that contains many terms, one for up, one for down, one for, as one single Lagrangian that contains this psi over here. That Lagrangian contains a new symmetry. This chiral symmetry over here becomes a more complex symmetry. Instead of being just U1, where you are individually rotating the up, the down, you are actually rotating the whole field made of massless quarks. And that's what generalizes to, for example, having SUNF, where this is the number of massless flavors that you are considering. So the QCD Lagrangian has a global symmetry. So this is a global symmetry because this parameter is simply a phase. It does not depend on the space-time. This is another global symmetry called chiral symmetry. And in the case of QCD, often we want to analyze QCD as having a global chiral symmetry that is more complex. Instead of just doing a simple phase field by field, we lump them together, and when we consider this SUNF. And then we have SUNF for the left fields and a whole SUNF for the right-handed fields as well. Okay. So yeah, it's a good question.
And the last one, is there a good reason that why there are no massless fermions in nature?
Very good. So as far as we know, there could still be one neutrino that is massless. Neutrinos are another story, right? Maybe we can pose this question until tomorrow. The reason is that all these standard model fields do interact with the Higgs. And whenever the Higgs does its business, that we will discuss tomorrow, it gives a mass to all fermions, except the neutrinos. This is the exception. So all charged fields, all the Dirac fields that we have in the standard model do have a mass, and their mass comes from the Higgs mechanism that we will discuss tomorrow.
Okay, very good. Thank you.
Okay, so I'm going to then move quite quickly to forces, because it's really, I'm sure you guys have seen some quantum field theory. I'm sure you've been told of stuff like if you want to account for forces, what you have to do is you take your fermion field that has this derivative, normal derivative, that has the mu and gamma mu. And what you are going to do is to promote this derivative to a covariant derivative. And this covariant derivative contains not just the normal derivative, but some interaction with a new field, with gauge bosons. No? Probably you've been told this way. Then you go from your free fermion field to a new Lagrangian that contains, sorry, there's I's, I never remember, a new term that contains interactions. So you go from simply describing the propagation of electrons and positrons with a possible mass to go and describe through this covariant derivative and this term over here possible interactions with a photon. You've probably been told that way. So let's promote the derivative to a covariant derivative that describes the interaction and on. Obviously, this is a unique consequence of symmetry. So let's see how this happens. Finally, we are going to understand why this has to be the case. So it all starts simply by saying, okay, so I know that this Lagrangian, including the mass, if I want, let's put the mass here, has a global symmetry. Has this symmetry where I take psi and I do exponential of I theta psi. And I know that this is a symmetry of my theory and it all works very well. And for that, it was important that this phi over here, this phase, is a constant. It's just simply a reparametrization through a phase. Why? Because whereas to the mass term, we don't care. If we take the mass term and we do this modification, we will get mass term, exponential of minus I psi, exponential of I psi, psi bar psi, and this goes away. To the derivative term, that this phase is constant is important, because if we now say, let's try to promote this phase, this transformation that is simply one overall phase everywhere in space-time, let's try to modify the fields in a way that depends on space and time. If we do that, the mass term will still be invariant. It's still a good symmetry of the mass of a Dirac fermion, but of course this derivative mu gamma mu over here is going to screw up things, because we are going to get I times exponential of I theta, now depends on x mu, psi bar with a minus. We get gamma mu, and we get a derivative that is acting on this exponential of I theta that depends on x mu psi. So when we try to enlarge the type of symmetries we are thinking on from global to local, or also called gauge, it's exactly the same. When we try to think of more general ways of transforming our fields, we get that the Lagrangian has a term minus I theta, psi bar, gamma mu, I theta d mu psi. So when the derivative acts on this, these two guys do cancel with each other, but then we get an overall, an additional thing that has to do with the derivative of this field. So that this phase depends on space-time. This local structure of this phase makes it, or it screws up, if you want, the invariance of the Lagrangian. Now my Lagrangian under this transformation transforms as what we had before, so that term and that term, plus an additional term, which is simply exponential of I theta times psi bar gamma mu psi and derivative mu theta. So this is non-zero, and that means that this is not a good symmetry of my Lagrangian. So this transformation, when I try to enhance it from simply global to local, is not a good symmetry of my Lagrangian. Okay, so one could say, well, since it's not a symmetry, we don't care. But of course, we don't do these kind of things. We don't give up. We like to explore and try to break things. So one of the things we do is to say, okay, fine. So if I take my matter field and my Lagrangian, and I try to think on all possible transformations that I could do, I see that there is a global symmetry that leads to lots of interesting consequences. So if I take in space-time my field and see what kind of transformations I can do on that field, an overall phase transformation leads to exactly the same laws of physics. So that is a good symmetry. But if I now try to do a transformation that depends on the position, that doesn't work. The laws of physics are not preserved. Okay, but then let's ask the question, what if I really wanted this to be possible? What if I really wanted to be able to consider transformations of my matter fields that depend on space-time? So what we are going to see is that the only way to make that consistent is actually, or assume that there is a symmetry that is local or gauge, exactly the same, is to precisely impose the presence of new degrees of freedom. So I can make that part happen. I can assume that there is something going on that my theory, nature, has more interesting symmetries, local symmetries, as long as I introduce new degrees of freedom. Why? Because I know that my Lagrangian, with only fermions, under these local symmetry transformations, does not transform properly. It does have a different from zero transformation. So it's not a symmetry of that Lagrangian with only fermions. So what if I try to introduce a new field, a new degree of freedom, whose transformations are precisely made up to cancel this guy? It looks quite contrived, right? But think about the logic. The logic is that you want to examine, you want to explore possibilities for symmetries of your theory. What you know is that there are electrons, there are things, things are happening. You have these matter fields that you can actually produce and see and so on. And you would like to see this Dirac field, whether there are more possibilities for this Dirac field. And when trying to go from the global symmetry of fermion number and so on to something local, you realize that the only way to make it happen is to actually introduce a Lagrangian now containing new fields. You know the story then. That's precisely what happens if I take a field, and in this case it has to be vectorial. that has particular properties, a field that when it's transformed goes to the original field plus I times something that is proportional to the derivative mu of theta, then this delta psi due to the electrons or to the fields plus the delta psi due to this vector field will actually cancel with each other. The simplest way that you've been told about is simply imposing that the derivative goes to a covariant derivative in exactly that way. So a simple substitution where d mu goes to I times some constant. It could be any constant, it's up to you. But this field that, of course, it has to have exactly the same properties. It has to be a vector, a quadrivector, under Lorentz transformations. And same story. Once you say, okay, in order to fix the fermion Lagrangian, I need a vector guy that has these particular transformations, then the only way to write the kinetic term for that vector field is precisely the form that you've been told about. It's the only way that is consistent. You see, the logic is we knew, Dirac and so on, that they were fermion fields, that they behave in a particular way. They had an equation. We started thinking about this equation as a consequence of Lorentz invariance. We then realized that the Dirac equation is the only thing we could write. Once we step above that, when we realize that there is an additional symmetries, internal symmetries related to that Lagrangian, which are these global symmetries. And then we realize these are the typical fermion number and so on, an electric charge that we knew about already from electromagnetism. But then introducing the photon, understanding how the photon acts on these electrons, comes from trying to enhance this global symmetry to a gauge symmetry, a local symmetry. And the only way to do that is to precisely have a field of vector nature whose transformation precisely cancels wherever was messed around with a fermion field. And once you have this kind of transformation, there is only one type of kinetic term that you can write down. All right. So we realize that the photon and the interactions of the photon with electrons are unique, and they are a consequence of a symmetry. It's a U1 symmetry, which was before global, but making it local, then imposed the emergence of new degrees of freedom. Those new degrees of freedom are these guys, the photons. And because they are degrees of freedom, they need to propagate, and their propagation properties are precisely this F mu nu that you knew of. The only thing you can write down consistent with these symmetry properties. Later on also, you realize that you could have imposed these photons by saying that the photon, in this case, corresponds, or the symmetry properties are actually corresponds to the adjoint representation of the symmetry group. In this case, is the U1, and so on and so forth. And you've probably also been told about, this is for abelian theories. For non-abelian theories, you know the story is a tiny bit more complicated. You need to introduce not only this term with a simple phase that depends on space-time, but a structure, right? So for example, when you think on SU2 symmetries, SU2 left of the standard model, then you have to think on vector bosons that now have here a label A123, that is precisely the SU2 indices. And this 1, 2, 3, this W bosons, W1, 2, and 3, plus the photon, A mu, are precisely the guys that is going to lead to the W's, the Z's, and the photon. We will see all this tomorrow because the way they interact with each other, there's U2 left cross U1 hypercharge, and how this leads to U1 electromagnetism is something that is, determined by the Higgs mechanism. All right. So I think I'm going to stop here. I could tell you more about forces, about the structure of non-abelian gauge theories, but you've probably seen this, and the only thing that it does is your covariant derivative is going to be exactly the same, and this F mu nu is just going to have self-interactions that lead to interesting situations. So in non-abelian theories, the gauge bosons can interact with each other. Whereas in abelian theories, like electromagnetism, the photons do not interact with each other. So those kinds of interactions are only possible in non-abelian groups. U1 is abelian, and SU2 is non-abelian. And having these self-interactions is important as well because it leads to processes or phenomena that we know, like for example, the screening of the electroweak interactions. Okay? But since I assume you've seen this in some form, the only, let's say, new piece of information is that this God-given transformation is the only thing you could do to enhance a global symmetry for your matter fields to a gauge symmetry. And that's the entry we had to understand forces. So forces in nature are simply a consequence of trying to think on the behavior of our fields, of our Dirac fields, that are invariant under a reparametrization of the fields that depends on space-time. And you have to have forces. You could turn it around and say that forces are a manifestation of nature's invariance under local reparametrizations of space-time. They are a manifestation. They are not just something that, let's say, you have to impose. They are a consequence of that symmetry and the fact that you believe that there is a global symmetry at play. And I'm stopping here. And tomorrow we'll just talk about electroweak symmetry breaking in general, Goldstone theorem, things that are not only important for the standard model, but also for any model of new physics with new light degrees of freedom.
Just before concluding, Veronica, there's a question.
Yeah.
Is there a specific reason why we choose a vector field to impose as the new degrees of freedom? Can another kind of field help to solve the problem?
So when you look at the structure here, sorry, before when we do this transformation of the Dirac field, I told you that there was a remaining term in your Lagrangian, and that it was screwing up the symmetry, right? The symmetry properties of your Lagrangian. So this local symmetry is not a good symmetry in your Lagrangian with only fermion fields. And this remaining thing was something like that went like I psi bar gamma mu psi, and then there was a derivative mu of your theta or your phase, if you want. So we needed something whose transformation properties, this additional degree of freedom, has to have the opposite effect as this d mu theta. So d mu theta that now depends on x mu. This guy is a vector quantity under the Lorentz invariance. So whatever that we want to introduce as new degrees of freedom probably is going to have to be a vector. And this is indeed the case. The thing that in the most simple way solves the problem is to introduce a new vector. This guy here already has the good Lorentz properties so that its variation is precisely made up to cancel the one of the fermions. So to answer your question, the vector field, the forces in the adjoint representation and so on is our way to introduce forces. It's the simplest way, and it's the way that we have indeed seen that is the correct one. But you could imagine other ways of doing this. Indeed, for example, you could imagine more complicated ways of, for example, introducing tensor fields that do a similar behavior. But you always end up with some kind of tuning, whereas these forces as gauge symmetries is like the simplest thing you could think of, and nature tends to do simple things.
And there's another question. Could we have explained pion interactions in this way by gauging the U1 times SU2 nucleon transformation?
Very good. So you say that the nuclear interactions where SU2 cross U1 global, right?
Yes.
Where this has to do with isospin, and this has to do or have to do with, in this case, baryon number. That's something I also wanted to tell you. When I wrote SU2 left, we are seeing the standard model from the point of view of symmetries, because they are such they are common thread everywhere, and they in fact behind all the predictivity that we have in the standard model. But there is a risk with that. A risk as humans, no, is that because the groups that appear are always the same. There is SU1, there is SU2, and in the color sector and SU3. Ooh, that's wow. But it's always like the simplest, lowest grade kind of groups that you could think of. There is a risk of confusing yourself. For example, yes, indeed, I write SU2 left, and you might have thought, that's the SU2 left of yesterday, where you were talking about SO3, 1 is equals SU2 left, SU2 left. No, here we are kind of abusing notation, because SU3, 1 that has this double covering, to left, right? This is a space-time transformation acting on a space-time. And it's SU2 left and SU2 right as a space-time transformation. It's just another way of acting on 4 vectors. That we use this structure, this common structure, to write things that are consistent, yes. So for example, this is a global symmetry, SU2 hypercharge and U1 baryon number, and you could indeed think on going and partly gauging maybe baryon number or the or the isospin and so on, in order to embed the nuclear interactions into a new sector. And this is this often done. So when people want to think about the, for example, a hypercharge, you can think on partly gauging U1 B minus L. So you can take a global symmetry of your theory, and all this, by the way, partly gauging is something I'm going to explain tomorrow. But you can take a global symmetry, like we've done with the simple fermion number symmetry of our Dirac fermion, and gauging it, which is making it local and seeing what are the consequences. So we do this all the time in border building. We impose some symmetry, or we try to get a new symmetry that leads to the presence of new degrees of freedom, which leads to new experimental consequences. Or we go the other way around. We see new degrees of freedom, and we try to link those degrees of freedom as a manifestation of a higher principle, which is some new symmetry principle. A long story just to say, yes, this is SU2, and this is SU2, and this is SU2. But in principle, those are different SU2s. But the fact they are the same group can actually help you later on trying to link them together and write consistent interactions. The same way we've done for nucleons and pions. We had SU2 of one type, we have O3 of another type, but we used this similarity, this isomorphism, to write a consistent interaction.
But in case this SU2 for the the isospin is broken due to the masses, so it will not be a good symmetry of a good gauge symmetry from this point of view.
Exactly.
And there is a question related to this. Can you give us some example of consequences caused by the breaking of SU2 due to the mass difference?
Yeah, the same in this case is okay, so let's say of nuclear interaction, we were saying d mu, j mu will be 0 if the masses were the same. But since they are not the same, this is non-zero, right? This current is no longer conserved. So the whole story about, for example, we could have spin interactions, the splitting of the spectrum, the selection rules are going to be violated. But this violation is going to be proportional to the mass difference, to electromagnetic interactions, because that's what makes any difference between the protons and the neutrons. So yeah, it means that you can take your nuclear theory and compute QED corrections to this nuclear theory and account for this breaking.
Okay, I don't see any other question. I think that we can stop here. So thanks again, Veronica, for this class. And
see you tomorrow for the last class. I'm sure you would be looking forward to finish. Hasta luego.
Thanks a lot. Bye.